Okay, I'm going to start recording officially so I can capture reminders and things. So yes, 2 more weeks after this, folks, of classes. I know, we're counting down. It's exciting. One thing I forgot to mention, on Monday, I need to leave office hours by 4:10 instead of 4:30 so I can accompany Vladimir to his TA award ceremony. So I told the other class that too, by the way, since most of them know you, so you may get some other folks, wishing you well.
Thank you.
So the Zoomers say congratulations again. Yes, so I will be doing that. Big homework 4 is due on Monday. 3/4 complete with respect to points attempted. It doesn't have to be perfect, but it does have to be turned in. So if you get to the point where you're stuck on something, you can write comments, like we can have a little dialogue. I wasn't sure about this, but here's my best, try. Like, that's fine at this stage. And I will try to get you feedback within a week or so that you'll have hopefully about 10 days to turn it back around if you feel like doing a revision. Revisions are optional. So if you look at your point totals and you're like, yeah, I have other fish to fry, you can keep your 1.5 or whatever, that's fine. I understand that, and that's totally fine. If you want to revise and fix whatever I asked, please leave my comments in and use track changes. That way I can see what I asked you to fix and what you did. Because that's protection not just for me, but for you. Because sometimes on revisions, I'll catch something that I didn't catch the first time. And that's not fair to ask you to have fixed something that expect you to fix something I didn't identify. So if I missed it the first time, then you win. But if I don't have that to compare to, then I don't know what I said. So you can mark the comments as resolved so that you can sort of check them off your list, but I just want to be able to open them and check to see what I had asked about. All the materials for the rest of the semester are up. So we have lecture 6 on path analysis to begin next week. Example 6A, which is what your last homework is going to be about. So homework 5 will be released probably next week, I would say. And that is a path analysis. So you will have one model. It'll be a big one, but one model. Yes. And that will be using M+ software. So please make sure that you have access to that through the virtual desktop if you have not already done so. Bridge 4 does not exist yet. I'm aiming to get that to Vladimir hopefully tomorrow or possibly Monday. He will check it and then I'll release it on Tuesday. So that's it. So we're getting there. In terms of finals week, no classes, no tests, no nothing, just office hours. So I will be in office hours my regular time on Monday and Wednesday, and then the time I would have been teaching on Tuesday, Thursday, 12:30 to 3:30 inclusive, I'll be in office hours. So ollie oxen free. If there's anything that you haven't gotten done, come on down. Let's get everybody finished. On Thursday night of finals week, everything closes. So, and I will submit whatever grade you've earned at that point. So everything that is outstanding must be done by Thursday, so I can get to grading, because our grades have to be turned in by Tuesday.
That's fast.
Yeah.
Especially if you have projects.
Yes, it is. So it's for my protection as well as your own. Any questions on work, due dates, etc.? Yes?
Everybody has slightly different how they want to. So let's say that I wanted to do a revision, okay? And let's say that I got it done a week after or earlier than the due date. Are you going to look at the revision earlier, or are you going to wait till everybody's done and then start looking at all the revisions at once?
I like to do them earlier if I can.
Okay.
So then they don't all pile up as much.
Well, like I said, but everybody has different thoughts, and thank you.
Yes, that is my intent.
I won't hold you to anything.
Yeah.
Just,
but that depends on how many folks need my attention. So.
very good.
As perspective, I have 11 projects happening in the other class, and there are 20 of you doing individual data analyses at the same time. So right now my head is a sea of data sets. So if you come and talk to me about your data, you probably will need to give me some context to help me remember which particular data set I should be remembering in this moment in time. You're welcome. And that's a politer response. I was thinking most of you probably hate me right now, but I'm okay with that. Because eventually, right, when you look back on this and you have practice and you have resources to take with you in the future, then hopefully maybe it's less painful. But I know this is crunch time for all of us right now. So I'm looking forward to seeing what you come up with. I hope this is useful. And at the very least, I hope this builds some confidence that, like, when you need to do this for real, you can. That's really the most important thing, is being able to take these skills and put them into action. So, alrighty then. Anything else in terms of due dates, logistics, reminders? Vladimir, am I forgetting anything from your end?
I was wondering, because example 6C is what we did last year.
Yes, it's yours.
Yes. Do you want me to do something with that?
I don't think we're gonna have time again, so I didn't want you to fuss with it, I just put it up.
Great. Yes.
So, yes, so 6A is what homework 5 is gonna be about. That is path models assuming normal outcomes. And then 6B and C are generalized versions, where I have a path model ending in binary outcomes, and then Vladimir made one with nominal outcomes. So
So
we
are there
have examples of that.
Bonus material, so to speak?
We'll see. We'll see how much I can
Well,
get through in class.
whatever you get to, but everything we need will be in 6A.
Correct.
To complete homework 5.
Yes.
So I'm gonna call it happy bonus material.
Yeah, if I don't get through it, it's bonus material, and if I do, then we'll talk. But
Cool.
I don't think we've ever gotten to 6C. Like, that just hasn't happened. And 6B, I think I spent like 10 minutes on last year. It was, like being on a game show and you're just trying to get through as fast as possible. But,
I do find it really helpful to spend more time on the foundations.
yeah,
Really understand it, and then if I have a good foundation, I can go explore more on my own.
I agree.
But when we introduce like a totally new idea, I feel like my brain is just in panic mode, and then you talk me through the panic, and then it's like, oh, again, like having those hooks to hang things on, and then you can act on that.
indeed. So yes, I have to be a little bit choosy at this point, how we spend the time that's remaining. I would rather you have a more solid foundation to build on for the future than to have seen examples of every possible kind of thing you could ever need to do.
A better set of Legos.
A better set of Legos, exactly, yeah. These are Legos. Because guess what? Do you know what, like, item response theory is? This!
Mhm.
It's latent variables predicting logits. And if you have an ordinal model for polytomous IRT, that's latent variables predicting cumulative logits. And nominal IRT is latent variables predicting baseline logits. It's all the same. So once you understand like how link functions work, they will show up in a bunch of different places. And that's why this class, I think, is especially useful to take prior to the structural equation modeling class. My version of it treats all of that from a generalized perspective. So we start with confirmatory factor models, which assume responses are continuous. Spoiler alert, they never are. And then switch over into IRT/IFA, which are two different versions of the same idea, and then into the SEM territory. So it's going to come back, is what I'm saying. It's all going to come back. Speaking of coming back, y'all came back. So how about we talk about some multivariate stuff? That sound good? All right. Making sure my recording is still on. Zoomers, I'm assuming you can hear me and see me okay? See the screen and all that good stuff? Thumbs? All right, thank you very much. We were talking about different ways of setting up the fixed effects to tell you different things. That's where I'd like to pick back up. So there are two different, I'm going to call this is a fancy word, parameterizations. That means how you set up the model. Or model specification would be another word. You have choices. And there's not necessarily an answer that's always right or always wrong. It depends on what you want to know. And generally speaking, it is advantageous to set up your model so that as many things you want to know are directly provided by the model as possible. And the things that are less of importance to you are linear combinations that you can get after the fact should you need them. So we talked about two different ways of doing this. Each of these is going to rely on a series of binary contrasts that is in stacked data. So do you remember that part, what I mean by stacked data or long data? Yes, you take a row of data. I have to do gestures. So a row of data and do this for each one, like that, transposed by person. So then it is one row per outcome per person, which is what we had before, right? If you fit a regression model to a data set, it's one row per outcome per person because each person has one outcome. We just have to make it so that all the outcomes are in one column, and then we use these binary switches to say, hey, if this is outcome A, turn these fixed effects on by multiplying them by this indicator variable. So then if it's B and C in the row, then those fixed effects are multiplied by 0, shutting them off. And then the same thing happens for B and for C. So with this sort of switch system, we can stick with the types of models that we already have seen, in which you have one global or general fixed intercept. That then is for a reference outcome. So DV is my abbreviation for dependent variable, or outcome in this case. And anything else that for the non-reference DVs becomes linear combinations. The alternative, which I think is maybe more difficult initially but becomes more intuitive very quickly, is to allow each outcome to have its own intercept and its own sets of fixed effects. And that is more useful if you are truly thinking about these as like 3 different outcomes as opposed to 3 different flavors of the same outcome. So let me give you some examples. So Rebecca, I'm going to call on you. You have a writing task, 4 writing tasks that people are supposed to do. And what kind of writing are they doing?
Integrated writing, so source-based writing. Source-based.
Source-based writing is one.
All 4 of them.
Oh, all 4 of them
Source-based
are.
writing. Sorry, I didn't understand the question.
Yeah.
They summarize 2 reading passages, then they summarize a listening passage, then they write an argument based on all 3.
Okay, so 3 different kinds of writing tasks. And you're interested how, if there's mean differences in how well they perform on this task, for instance. So if that's what you want to know, then you would set it up as a general intercept model where one of your tasks is the reference, and your slopes give you mean differences to get to each of the others. And then you can ask, like, are people who are, more educated better at this task than that one? Like, you can have slopes that predict the reference task and then moderate the differences. So, like, the task difference might be bigger for some kinds of people than others. Like, that's what I would do in your case. If you're thinking of it as, like, I have 3 different outcomes, period. So, like, I keep going back to the clinical version since I'm staring at the folks from counseling here. We have, like, anxiety as a measure, depression as a measure, and, say, negative affect. And I want to know how some intervention, for instance, improves these outcomes. Like, I wouldn't have a question like, do you have more anxiety than you have depression? Like, that doesn't mean differences don't make any sense in that category. So you're thinking of them as like 3 separate things. Then it makes more sense to set up the model the second way, where each intercept and all the slopes of your predictors is DV specific. Then you get, and that is how path models are set up as well. So we talked about the first one, we hadn't yet talked about the second one. This is just to say that you don't have to actually physically make these 3 variables. If you treat your outcome variable as a factor variable in terms of which one it is, it will make them for you. So in R, for instance, a factor variable creates these internal contrasts under the hood that are then listed in your output. So it can save you a little bit of coding if you have a whole bunch of different types of outcomes at the same time and you don't want to make like 10 dummy codes. But it can also be less transparent what's happening. So I tend not to do it that way. So we looked at this version last time, where the empty model, so this is my predicted Y for my individual, and then for which DV, so I'm picking up a second subscript in this mutation scheme, is a general intercept. General intercept means there's nothing multiplying it. Okay, so this is an additive thing that starts off each person's prediction, regardless of which row of data you're talking about. Question?
No, so that'd be like our 1. And you know how we had the reference 1 for our typical intercept.
Yes, yeah, like there's an implied
Yes.
1 that multiplies it. And
Yes.
so in the code, when you're making linear combinations, you put a 1 there if you
Right.
want that intercept to be turned on.
Right.
And these are indicators for whether it's A, that's a 1 if it's A, and 0 otherwise, and 1 if it's B for this one. So even though these look like slopes, they're intercepts. Like functionally speaking, this gives us 3 intercepts. It builds it as, what is it for C plus how it differs for A, and then what is it for C plus how it differs for B. So these are differences. Like, these are the differences between your tasks. And so that then sets up the idea that each task, for instance, would have a different mean. When we include predictors in the model, so X as a generic person level variable, so this would be a person characteristic, that's why it only gets an I. It's not outcome specific in these models. The main effect of X here is the simple main effect, or conditional, when these interaction terms are 0. So therefore, these 0 out if we're talking about DVC. This becomes the main effect of X specifically in predicting the C outcome. These slopes, beta 1, 1 and beta 1, 2, then give us the difference in how X predicts the other outcomes. So it moderates the mean difference between tasks in the example that we're working with. So this would be like 3 tasks in this story. And if you want to know what the slope is when you're predicting A, or what it is when you're predicting B, you would start with what it is when it's predicting C, plus how it differs for A. And so that combination then gives you the outcome-specific slope of this predictor. So I think that's where we left off. This is what it would look like in code. So you can either write out the indicator variables, so C is like the implied reference here, or you can do it as a factor variable, so this is SAS. In Stata, it would be I, and then B last changes the reference to be the last one. So it's consistent across Stata and SAS here. And then R would be the same way, except you would say that DV is a factor in this case, or you could write them out this way. So does this make sense so far as one way of thinking about it? This is the usual way we're used to thinking about it. Okay, let me show you the alternative. This is the DV specific version, where everything in the model is going to multiply one of these indicator variables. So we don't have a beta 00 sitting all by itself times 1. It's times a variable. So this is the intercept for C, this is the intercept for A, and this is the intercept for B.
Would you use this, like, let's say, for example, you had 3 variables that you thought were doing the same thing, but you weren't sure? Could you make a model in which you treated each of those having their own intercepts to see how the rest of the effects were impacted by doing that, or not?
Well, as long as you allow each outcome to have a separate intercept and separate fixed slopes of your predictors, then it's 6 of one, half dozen of the other. You can rearrange the models to make them equivalent. It's just a question of which slopes are by default part of your model and which ones are linear combinations.
Okay.
You can always get all the information, though, if you're willing to do it.
Yeah. There's lots of different, okay,
Yeah.
cool.
Yeah.
Alrighty.
So this is different. Okay, this is different. To do this, you have to remove the general intercept from the model, and I'll show you what that looks like in code in just a second. So in the example I'm going to show you, we're predicting attitudes in family members where I have a mom outcome, a dad outcome, and a kid outcome. So this is the type of model I think that is most intuitive. What's the intercept for dad? What's the intercept for mom? What's the intercept for kid? If I want to know the differences between them, those are the linear combinations I have to ask for. If I add a predictor, these look like interaction terms, but they're not. They're technically nested effects. And to make it more transparent as to what's actually happening, nested effects are notated in different ways. Think of these as switches. So beta 1.0 is the slope of x if I'm predicting the C outcome. Beta 1.1 is the slope of x if I'm predicting A. Beta 1.2 is the slope of x if I'm predicting B. So then I directly get the effect of x for each thing. If I want to know if x matters more when you're predicting A than B, or A than C, or whatnot, those are the linear combinations. So path analysis works this way.
Okay.
And I think it becomes more intuitive than trying to figure out differences between boxes and things. You're going to see boxes, that's why I keep talking about it. Path models literally are like boxes and arrows, but this is what's happening under the hood. And the code for it then, so in Stata, no constant shuts off the general intercept as an option after the comma. And in SAS, it is no int.
No intercept.
Exactly. And in R, you put a 0 where you would normally put a 1.
Turned it off.
Exactly.
Or, sorry, a 0 multiplier.
Yeah. So-
Do you know which way it interprets it, a 0 multiplier, or it just says no?
If I had to guess, it's the multiplier, because the 1 would be the multiplier otherwise.
All right, cool.
Yep. So the code is going to look a little bit different because of the requirement that we have to tell it, hey, A, B, and C that come from the same person, those get to be correlated. So that's what the rest of this is doing here, and I'll show, in the example, I'll show you more details on that, but this is just another example. It is possible to mix and match across different ways of setting it up, but it's it's more easily confused if you do that. So this is an example. Let's say that I have a general intercept version here. So this would be like I have 4 tasks or 3 tasks and I want to know about mean differences between them. So beta 01 and beta 02 would give me the mean differences across tasks. So I have x1 as a predictor here, and it would be specific to task C because of these interaction terms. This allows the effect of x1 to differ if I'm predicting A instead or B instead. But then look at where the hole is right here. I don't have a main effect of x2. So that changes the interpretation of these previously were interaction terms, they're nested effects now. Because there's no like reference x2 for these to deviate from. This is the effect of x2 on A, and this is the effect of x2 on B. So these 2 slopes right here, beta 1,1 and beta 1,2, these are differences in the slope of x1 across outcomes. These are the slope of x2 for each outcome. So it gets real tricky real quick, but you can kind of mix and match these things. And this same model will be represented this way here. And I think this makes it a little bit more clear that you don't have to have every predictor predict every outcome. They can be on for some and not others. That's much more easily accomplished in this DV-specific version. Some outcomes it may not be relevant for. You don't have to put it in. It's up to you. All right. Can I show you an example with numbers? Would that make it better? As opposed to letters?
Numbers are great.
Yeah, I don't think I could make it worse. Let's put it that way. So this is part 1. This is example 5. I just fixed the link a few minutes ago if you came up empty. So this is a real study. When I was a postdoc at Penn State, I got to know the folks in the Human Development and Family Studies program where I was in the Gerontology Center, which was affiliated with that, but they collected a whole lot of family data. And what made this particular data set interesting is that they had different perspectives on many stuff. So these are adults. So there's an adult child who was like the recruiting for the family, and they only took families that were intact in terms of still being together with the parents and heterosexual parents. So this is mom, dad, and adult child is the setup for this. I think these data were collected in the 90s or so, quite a while ago. What we are looking at as our outcome is their attitude on a scale measuring gender roles in marriage, where higher values indicate more conservative attitudes. So women are probably not supposed to do the things if you're scoring high on this task. I made it into a mean across items so that the range would be from 1 to 4. So this is an example of an outcome that doesn't fit neatly into one of our little generalized boxes. It has boundaries. If you answered 1 to every item, then your average will be 1. If you answered 4 to every item, your average will be 4. And if you answered ambiguously or heterogeneously, it'll be somewhere between the 2. So it's bounded, but it's continuous between 1 and 4. So I could trick that into a binomial by rescaling if I wanted to. I could pretend that it's continue-ish, and that's what I'm going to do here. Continue-ish to start with, and then we'll check some assumptions at the end of this. I am going to have only 2 predictors: the gender of the adult child and the years of education of each person in the family, measured such that 0 is 12 years. That's it. That's going to be a complicated enough story. In these models, we are going to use an unstructured R matrix. That term means that we are letting each person's outcome variance differ from each other. So dad gets a variance, mom gets a variance, the kid gets a variance. And all possible 3 covariances are estimated separately. We know that's going to fit the best in an absolute sense. Can't be wrong. That is analogous to MANOVA in least squares land. It is analogous to the saturated model if you've had any SEM training. Other choices are listed here. Compound symmetry heterogeneous is a pattern where each person gets a different variance, but it constrains the correlations among the residuals to be the same number. And compound symmetry further constrains the correlations to be the same across that. So we're going to predict 3 outcomes simultaneously. Part 1 is doing this within traditional univariate software like we've been using, where all the outcomes have to be in one column and we got to do the switches. Part 2 is going to pick up where this left off and show you how to do the same kind of modeling in a path model instead, which has some advantages, especially in this case. So the marginal outcome distributions showed some positive skew, meaning that most of the folks are towards the bottom of the scale choices and fewer are extra conservative. We're going to check on whether or not we end up with predicted outcomes that are out of bounds at the end of this, as well as what some residual plots and things look like. But our first order of business is to change the structure of the data. This is called stacking or reshaping. Reshape is the command in R and in Stata. So for instance, I've got 2 rows of data. So the unit of analysis for this study is the family. That's what's being measured repeatedly by asking multiple people from the same family the same questions. So family ID 3996, for instance, the adult child is, I have boy, a man, I guess. The child's education is 2. So given the centering, that is someone who probably has 14 years of education, maybe an associate's degree. Same is true of mom, same is true of dad. And then the kids' attitudes is a 1. So they're at the floor of the measure, they're not conservative. Mom is a little more conservative, dad's at the floor. And then this next family down here, we have the same information. So it is advantageous, by the way, even though education could be stored in one column, so it'd be like mine, 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 like that, it's advantageous to store it in separate columns. That way we can cross-predict. So I can see, for instance, if dad's education predicts mom's outcomes and vice versa. That is the basis of what is known as actor-partner models in the world of dyadic data. And I always have to make this gesture with it because you end up with like dyads, so it could be like a mom and a kid or 2 partners, and actor effects is like how my predictors predict my outcomes. And then partner effects is like how my predictor predicts your outcome and how your predictor affects my outcome. And so those are like crossed usually in diagram form. So you're able to do those kinds of analyses if you keep them in separate columns like this as a family level variable. But we can't analyze these data the way they are because outcomes are spread across 3 columns. We need to stack it. So the end result of the code that I'm going to show you next is a data set that would look like this, where now it is 3 rows per family. I have a new categorical or string variable that says which row goes with which kind of person. I have my dummy indicators, and rather than call them like DVA, DVB, I named them kid, mom, dad. 3 letters, easy to type. And now I have one column that is called marital, which holds the attitude scores for each of the people. Okay, with me so far, or questions about that?
So the family ID is the same across both the bride and mom.
Yes.
And
And
then
kid.
when you stack the data, you have to create a new variable which you label kid, mom, dad.
I created so the new variables in the file are the last ones from here over.
Oh, so there's multiple.
Yes, this is new. So this is a categorical variable that keeps track of which row goes with which type of outcome. And then I converted that into numeric data so that I could use the 0s and 1s as switches to turn on and off the fixed effects that would go into that row. Yeah. And notably, family ID, the gender of the adult child, and education just all get pasted down. And we need it that way because we need to have each row be complete to stay in the model. By the way, if you're working with data for these kinds of designs and you have some variables that are family level things and some variables that are people level things, you can merge the files together. You don't have to like manually copy the stuff down. If you let the software do it, it's much easier.
I know this is only pertaining to this particular model, but if a family had 3 kids,
Mhm.
would they then have 9 stacked? Or would they have 3 stacked? Or how would that look? Or just have 1 additional line per additional child?
1 additional line per additional child. And we don't know what the family composition is for the rest of their family. We just got 3 people to
No, I'm
represent
just-
the family.
Well,
in
okay,
the
I didn't
study.
know if there was only 3 people or sometimes you did have like 4.
Not in this example.
Okay.
It's limited to 3. But there could be other adult children or younger children lurking in the family that we didn't survey.
Okay.
Yeah. So this is the initial step, is to reshape the data, and then we can use it. So fortunately, Stata and R have built-in commands to do this, so long as you name your variables a certain way. And I spent probably an hour trying to find a workaround and eventually just gave up and renamed my variables. It's like, fine, you win, Stata. So my original variables were kid marital, mom marital, and dad marital. And it would not work with the code below. So I renamed them into marital 1, 2, and 3. Now Stata will understand, using a reshape command, which way do you want to go? Is it wide to long or long to wide? So long is where we're going, so that's what's next. Then you give it the stem of the variable. And then it looks for all the permutations that it has. So that's why it had to be 1, 2, 3, because they all had to have marital as the prefix of the name, or the stem. I is telling it how are the data to be organized. So what is the sample like indicator variable, so family ID in this case. And then J is what are you going to call the 1, 2, 3, and I named it dvnum for numeric dv. Then I created the dummy codes, so generating kid, mom, dad equal to 0, and then changing them to 1s if it's the first dv, the second dv, and the third dv. And then adding labels like the good data analyst I was trained to be. You can't label variables in R. It drives me insane. And there's some packages that will actually break if you try to use labeled variables, much to my chagrin. You don't need to worry about this in this example, but I wanted to remind you that this will happen in your life. Any row that is incomplete will not be used with respect to the variables that are in the model. So this is saying, okay, let's get a count for the number missing across all the variables I'm eventually going to need. If that number missing is greater than 0, remove the case. So I'm subsetting my data ahead of time so that no matter what my model has in it, the sample size stays the same. And if you're like, isn't it bad to remove data? Yes, it's very bad. But within this framework, that's the only choice we have. I'm going to show you a better way to do it next week. R code. So setting the working directory. This is a SAS data set in this example. It's not within your download since it's real data. And this is the wide version. So now I'm going to make it into the long version with a command that is base R called reshape. So it wants to know what data set, what direction, what's your ID variable, what are the columns that you're going to stack, what do you want it to be called, and then the time variable, and then what are the values. So you'd have a bunch of these in here if you had more than one column to stack. Yes?
Just to be clear, so what you were saying earlier about like kid marital, mom marital, dad marital, needing to be switched, so marital comes first, that was for Stata.
No, just for Stata.
That was not for R.
Yep. Yeah, R didn't care. R let me have my names as the way they were.
Okay.
Can you have two different variables that you're unstacking, and so that's like extra super huge, humongous, long unstacked table?
Yeah.
I know we're not dealing with it with this model, but like if you had marital and shoe size or something or whatever.
Yeah, then we would need, actually, I'd have to look for an example, but
Oh,
essentially you need like to understand like this set goes with this name, this set goes with that name, but you can add more layers to this, more names to this. Yep. You're not going to have to do this in your homework or anything,
No, I'm just.
but in your lives you might have to. And then the same indicator variables, kid, mom, dad, set to 0 initially, turned on to 1. And then I have complete cases as a base R function that does the same thing here. So it subsets the data to complete. All right, we ready to see some models?
Oh, sorry.
Not
Last question. The subsetting in R happens after you create variables.
Yes, after.
After you create
Yeah.
variables.
So like these were already in the data set, and they just got pasted down the rows. This is the new one, that's my outcome.
Okay, so after you reshape data with new variable names, subset data, so you just have to do the subsetting before you run the model,
Right.
not before you do it. Okay.
Yeah, and otherwise you would, like, it'll work, it's just that it will drop incomplete cases, and so then when you add this predictor, oh, now my sample size is this, oh, I add this predictor, now my sample size is that, that gets to be ugly to keep track of.
Okay.
So to make it consistent, I do this selection ahead of time. All right.
So, I did that in homework 4. Vladimir, did you tell me to do that?
Don't blame
Somebody
Vladimir.
told me. Okay.
Like it looks familiar.
Yeah. Okay, so model 0A in Stata,
That's
and then
the
an R.
model.
Yeah, it's the empty model.
Okay.
So it's two different versions. The general intercept version, so marital is my outcome. I have FI as my subscripts. Which family is it? And then which individual within the family. So individual is like DV here, because I'm thinking of my people as repeated measures of the family. So I've got a general intercept that's not being multiplied by anything. That means that beta 0 is going to predict all the rows of the data. Who's not in the model?
Dad.
Dad.
So that's
Okay,
dad.
that's dad's. That's what it's going to mean. So we're starting off everyone's prediction for marital with what dad said.
Mhm.
Then we're going to adjust it
To kid.
to get up to kid by a difference. And then if it's mom instead, we'll adjust it by that difference instead. So we get 3 means out of this in a roundabout sort of way.
Does ordering of the betas matter for interpretation?
Not really, but it matters in terms of how it shows up in your output. And so I try to write the equation to be consistent with the syntax in terms of how things are ordered. And this is my notation scheme that I've developed for this. Other people may have a different one. Like one that I often see for path models is they use a superscript to say like which outcome the parameter goes with. That gets confusing though if you think of it as an exponent.
I guess I'm just asking that, like, if father's the first intercept, is he become a reference?
He is the reference. And honestly, why I picked dad is because in SAS it defaults to the last one and dad was last. That I have no better reason than that. But in life, you can pick which one like you're thinking of as sort of the baseline and then how the other things differ. So like if it were, how well do you do on your homework in a control condition versus where there's no music playing versus listening to Metallica versus listening to classical music, right? Like the no music would be a logical like reference outcome. So then you talk about the effect of heavy metal, the effect of classical. I heard Metallica on the way to work today. That's why I'm just going with it.
So would the path model be a better model if you wanted to do something like that, so you could control what is what as opposed to trying to work with its default?
I think if you want to say, what happens to mom, what happens to dad, what happens to kid, then this is not the way to go. But if you're interested in thinking about like, how do I say this? I'm trying to make up a fancy word for it. Like the parental discrepancy, like as the construct, then that's exactly what beta 01 is telling me.
So this way is better to see like what kind of an impact mom and dad have on each other, so to speak.
No, this would be like
Or-
the differences in how conservative different people are.
Okay.
Can I think of something that in my head would make sense in this type of model? So if
Sure.
you're looking at a classroom and you want to measure the instructor's political views,
Okay.
and then they're the reference group, and then each kid gets their own model for like political views, and we see then how much the instructor influences the students. Would that be
Maybe, except that one is across levels, and so that introduces additional complications.
okay?
So like where this would be useful, the example I gave on Tuesday, like the stick figure scale of like how big you think your body is as actual is one outcome, and then what is your ideal body? That discrepancy of body dissatisfaction, the difference between the two, that's the construct.
Sure. Okay.
And so like this way of setting it up, this would be that construct directly, the difference between the two. And then you can say, is body dissatisfaction greater for people who have this characteristic than that characteristic? And that's an interaction term to answer that. So if I wanted to ask, are moms more conservative than dads? Are kids more conservative than dads? This is the way to go.
Yes, I was asking that to see to create a ladder between like the model and the research question.
Exactly. Yeah. It's 6 of one, half dozen of the other in terms of the math, because you can always get what's not directly implied as linear combinations. But it's more convenient if the stuff you care about shows up by default in your model.
And because of the use of our intercept here, it would be good to say whether or not it was significant or not, because this is a, like, dad, and it was like a significant predictor for dad or not?
In this case, the intercept will be tested against 0, which isn't even a possible value for the scale.
Gotcha,
So it better be different than 0.
right.
Whereas these being tested against 0 is the significance of how kids and dads differ,
Okay.
where
but-
0 as a null hypothesis would
right,
make sense.
But if we were using the path model instead, then that would be okay to interpret that as significant or not, because dad was his own column, so to speak, and mom and then kid.
In that case, so that's the way the next model is going to be set
Sorry,
up.
you're right, I'm sorry,
Yeah.
I know,
Yeah.
I'm sorry, I'm
So-
jumping ahead.
Yes, so let me do this one,
Listen,
because I
okay,
don't want to
I know.
flip back and forth, because it's already confusing enough, and it's, April, and I'm sensitive to the limited resources we are all working with at this point in time. Can I get an amen on that? All right, so this is more useful if you care about differences between outcomes as things, okay? Things you care about. So welcome to new commands. So Stata mixed is what we're using. That stands for mixed effects models. It also has these correlation patterns built in as an option. And this marital is my outcome. These are my indicator variables for kid and mom. So these columns right here. Bar family ID, colon, that's a new thing. That is how you tell Stata which outcomes go together as part of the same sampling unit. So family ID is the variable that's pasted down the columns. And when Stata sees this, it's automatically going to put in something called a random intercept, which I've not talked about yet and probably won't get to. You can hear more about that in the fall if you want to come back. And I don't want that in this case, so no constant takes that out. So the comments here, this no constant removes the random intercept. There's a separate one that will be added to remove the fixed intercept in the next model. And note these in Stata, it took me forever to understand this, and then it finally dawned on me. 3 lines is a line continuer. So that means keep reading, keep reading, keep reading, keep reading, we're not done yet. Because in Stata, there's nothing that like a semicolon or like a period that you put at the end to say you're done. So this says keep reading, keep reading. So from Stata's perspective, all of this is one command, one thing. And so to make it keep reading, to get all the options, you have 3 lines. But you can also put comments after it, and it will render those as comments. 2 is just a comment, not a line continuer.
Interesting.
Yeah. So this is a separate thing. This is a separate thing. And so the 2 means like you're done. Yeah. The newer versions of Stata, I think, don't require these. But to make sure my code is backwards compatible, I'm keeping them in. All right. So backing out again. No log means suppress the output that shows the iteration history. REML, that's new. This is residual maximum likelihood, which is the analog to ordinary least squares, but it allows missing data. So residuals, unstructured, like this. That is controlling the pattern of my variances and covariances of my outcomes. So unstructured means each outcome gets its own residual variance, and each pair of outcomes gets its own covariance. And how the outcomes are organized is with this ID number. So this is going to be 1, 2, 3 in the data set. The reason that I include that is because if missing data happens, like if I only have a 1 and a 3 for some families, without that variable, it'll be like, here's the first one, that must be 1. Here's the second row, that must be 2. But it's not, it's actually 3. So to make sure that they get in the right spots in the matrix, we use an ID variable to control for missing data. Difficult. I know.
It's just difficult.
It is an option that uses that adds start values. And I've found in particular for this type of model in Stata, it can like take minutes to finish. And so this hopefully will speed up estimation. Degrees of freedom, I'm going to wave my hands at that for right now. But essentially what's going to happen is that it's going to use denominator degrees of freedom in the same way that we would in a standard regression model. So we're back to that for these. -2 log likelihood is what I typically ask for in the homework system. Stata, here's some code that prints that for you. And then Lincoms, you've seen these before, right? So we have the first two are building, stop that. The first two are building the individual specific intercept for the non-reference outcomes. So for kid and mom in this case. And the last one, if you can see here, this is a -1 and a 1. Whenever you see that, that's a difference. So I'm asking essentially, do mom and kid differ in their intercepts? Differences among the non-reference outcomes. Okay,
Lots of stuff.
lots of stuff. So more stuff than usual. How many observations? 420. Number of groups? 140. So 140 families. Each of them has 3 observations, creating 420 observations in total. So check this first to make sure it understands your data, because if these numbers are wrong, you're done. Stop. Got to fix it. And then we get into the number. So in this case, all families have 3. It gives us an F test, so we're back to F, because we're back in normal land, just for a week or so. An F test for the 2 slopes. So it looks like, yeah, mom, there's some differences across the 3 people in their levels of conservative attitudes. Var E1, Var E2, Var E3. That is the variance of DV1, DV2, DV3.
And that's because we asked for all of them to have different variances, yes.
Exactly. So that was activated by this little piece right here, DV_num as the indicator variable, and then unstructured as the pattern. So just eyeballing these, they kind of look like they'd be pretty close. But I'm going to leave them separate. And then, yes, this is me being nice, trying to label these things for you. This is not Stata. Then if you want the correlation pattern, so here is the variance covariance matrix that has organized these 6 numbers into a matrix. So the variance on the diagonal, on the off diagonal are covariances. We can't interpret those without knowing the scale, so we can interpret correlations the same. So this is the first piece of information that you might care about. How related are people's outcomes from the same family? So it looks like there is a stronger relationship between mom and dad than with the kid. Slightly, but enough. R, folks, your code's a little bit of a mess. Sorry, that's R. This is the only package I found that will do this. So we have GLS, that stands for generalized least squares. Tell it the data set. REML is the estimator. Here's my model. That part looks the same. So marital is the column that has all 3 outcomes. This is the model that has a general intercept, so I got my 1. And then kid and mom are my predictor columns. This part, I had to get an example that Jonathan did. I never would have figured this out otherwise. Correlation equals core sim form equals squiggle DV_num bar family ID. That is a long way of saying I'd like all separate correlations across my outcomes, please. And my outcomes are organized within families by this ID variable.
It's sort of like a conditional statement.
Yeah,
So I'm just saying.
I don't know. I made it work. That's what I can say.
Yeah.
And then weights, you might think that that refers to sampling weights or something. No, that's heterogeneity of variance. This means I'd like each outcome to have a separate variance, please. So these 2 together create an unstructured matrix. The output that it gives is very weird. It gives you multipliers of standard deviations. And so I was like, oh no, we're not doing this. So I found a way to get it to print things. So getVarCov is a function that prints the actual variances and covariances of your outcomes, where the variances are on the diagonal, covariances are on the off diagonal. Core matrix turns that into a correlation, and so then this is the correlation matrix among my outcomes. To get the same F test that Stata provided for the 2 slopes that are in my model that differentiate the 3 means, I did that with GLHT. I don't know if we've seen one that looks like this before. Does this look familiar?
No,
This might be
we'll see.
new.
Ooh.
Yeah. Okay, so this part says Hey, I'd like the kid slope, please. And then a comma, very important. And this is, I'd like the mom slope, please. So this is not adding the slopes together. This is a joint hypothesis test of whether they're both 0 at the same time.
Isn't it right to think of that as like a submodel test?
This is analogous to the F-test for the regression model, like the ANOVA table for the model in regression. This is the analog to that. I'm doing it manually because it wouldn't spit out otherwise. Interestingly, I got an error message. It was like, you can't have an F. No, here's a chi-square instead. Now, does that seem weird that it gave me a chi-square instead of an F? The difference is whether you're using denominator degrees of freedom. If you are, it's F is the reference distribution to get a p-value. If you aren't, then it's chi-square. However, I went through the object saved from the model in the environment, and I found the F. It wouldn't print it.
You found it, but didn't want to give it to you.
And I was like, oh, hell no, I'm going to print it. So I found it, figured out where it was, and there it is. So, by the way, F times the number of slopes that you're testing simultaneously is chi-square. F is a per slope metric and chi-square is not. So either way, there are mean differences across the three kinds of people. Yes.
Could you scroll up just a little bit for the degrees of freedom? Did we get that because it was you have one fixed effect and you had only 140 true observations, even though we pulled it into 420?
Yeah, the 139 is, I know it's a little hokey, but like per outcome, we used one fixed effect.
Okay.
And that's how it's computing, because we have 140 families.
Okay.
Yep. Question?
So, for homework 4, I am using some categorical predictors. Can I do this like two C-bind things, R-bind things, in order to get the cumulative effect of all of the categorical options? So, for example, I'm comparing 3 universities. So, in my model for my boarding home regression, I have 2 slopes in my model, 1 for 0 versus 1, 1 for 0 versus 2. So, I wanted to try to get like one F-test for like the overall effect of the university. But
Yes.
I didn't know how.
Yes, you can. So the question was an example of having a categorical predictor with 3 levels or 4? How many?
3 universities, so I have 2 slopes. for
Okay.
3.
So just like in this case, a categorical predictor with 3 levels, and that requires 2 slopes to differentiate them. So if you want a joint test of like, does this predictor matter, you can do it this way. This works for any kind of slope, not just ones for categorical predictors, but if you were to let R treat university as a factor variable, then it will not only build the contrast for you that you built manually, but you can use the ANOVA function as a follow-up and get an F-test for the factor variable contrast as a set. So then it's less typing, potentially.
But I need to be careful with that because if I try to treat my university predictor as a factor variable and I've already run it separately with several slopes for each one, it's going to mess up my calculations, right?
Yeah, it'd be one or the other. It's redundant. It's redundant.
Okay.
It's like, do you want to do the setting up or do you want to let it do it under the hood?
Okay.
Under the hood is convenient, but it's also less transparent. Especially when you get into these models where you're taking out intercepts, you can get some weird stuff that comes back, where I'm not even sure what it's doing in some of the cases I've seen.
Okay, so currently I'm not using factor variables.
Yeah.
I did use ANOVA to do the overall F-test for the model. So there's a way that I can use ANOVA to do the same thing.
Yes, I believe you put like one model that doesn't have the categorical predictor and then one that does in the ANOVA function. Vladimir, is the sounding right? No, okay. I've seen examples of it, and then it's kind of like a nested model comparison type of deal. And so then it like figures out what's new in the next model and tests just the new contribution.
Oh, okay, thank you.
It is analogous to sequential regression, like when you have hierarchical regression, you have like a block of predictors and you get an F-test for the change in the block. That's what it's doing.
Okay. Okay, that's really helpful, thank you.
Yeah, there's always more than one way to get at something. I like this way even though it's a little tedious because you can go into any slope in your model and put them together in whatever way is informative to you. They don't have to be just parts of categories. All right, so let's see the answers. Here are the missing informations in another GLHT call. So these two are adding together the fixed intercept for dad plus the slope for how kid differs or mom differs to get the predicted intercept for those non-reference outcomes. And this is comparing the two slopes of kid and mom to see if they're different. So I pasted in SAS output because it was a lot neater and shorter, but it's structured the same way. So here's the estimates. So the intercept in this model is estimated as 1.95. That's the average rating from dads. So on a scale of 1 to 4, so they're like halfway up the scale. Kids have a slope of negative 0.3, so kids are less conservative on this scale of 1 to 4 by about 1/3 of a point on average. Moms are slightly less conservative than dads, but pretty darn close. So you can see the p-value for that. And then if you want to see what the three means actually are as linear combinations, these are the two for kid and mom that you get from adding those things together. And then the difference between these two is 0.27, and that is significant. So the story so far, mom and dad are similarly conservative, more so than their kid. That's what we've learned. Now the other version, the path model version. So now I don't have a general intercept. I have one for dad, one for kid, and one for mom. So there's going to be something multiplying every term in this model when you set it up this way. So if I'm in a row of data that's for dad, this one will turn on because dad is 1. But kid would be 0 and mom would be 0, so these would not contribute to the prediction of dad's score. They drop out, and the same would happen for the other outcomes. So it's as if we are running 3 regression models simultaneously. That's what we're doing. And you're like, why do I need to put them all together? Well, to answer questions like, how related are these outcomes? Are they still that related after I control for XYZ? Or to be able to do the crossover stuff, like how does dad's information predict the kid's outcome? Like we could do all of that kind of things at the same time. So in Stata, we have an extra no constant. So there's 2 of them. They're not redundant. One shuts off the fixed intercept, one shuts off the random intercept that I haven't told you about. In the model then, I've got all 3 of my indicator variables. And that means differences between them are linear combinations. So I'm asking for the 3 pairwise comparisons implied by these 3 means here. In R, it is analogous to what we had before. The only difference is right here. I shut off the fixed intercept by putting a 0 there. I now have to put in the dad outcome. So kid, mom, dad. Yeah, put it in that order. In the model, I have dad first for symmetry with the other ones. So then what I get, this is the predicted intercept or the mean for each kind of person. The end. I find this more intuitive.
Are those estimates the same or similar to what was given with the other model?
They are exactly the same.
Okay.
Because the other model gave us directly 1 mean and 2 mean differences. This one gave us 3 means. So there's 6 pieces of information that you would want to get out of it. 3 come by default. The other 3 are linear combinations. Just depends on which way you want to go.
Just
Yep.
me just trying to, I'm like, okay, so I don't have to say, I chose this model over this model because I'm still predicting similarly.
These are equivalent models. They are rearrangements of each other.
Okay.
Different parameterizations.
Yep.
Yes. So then the differences are the linear combinations, and I asked for those down here. So because I find this more intuitive and because I know we're heading into path analysis, we're going to go DV-specific intercepts. And because I knew it was April, I'm highlighting what's changed at every step. So first question, I'm using a characteristic of the adult child, their binary gender in this example, to predict everyone's outcomes. So are adult men more conservative than adult women as the child of focus in the family? And then if I'm I guess they would call it now what, a girl dad or boy dad, that's a thing they say now. It's a thing, I've seen t-shirts. Then am I different? Now this is admittedly kind of silly because I don't know about the rest of their family and they could be a girl dad and a boy dad at the same time, but we're just focusing on one kid. So I'm adding it in a similar fashion. So note there is no main effect of kid's gender. Every place it's attached to one of these indicator variables. So this is the effect of the kid's gender predicting the dad's outcome. The next one is the kid's gender predicting the kid's outcome, and then the kid's gender predicting the mom's outcome. So we set those up as interaction terms, but they're not. They are main effects. They are DV-specific main effects. They just look like interaction terms at this point.
Because our intercepts are that first row.
That's right. So these are the fixed intercepts. These are the main effects of the adult child's gender on each person, separately. I don't have the output. I think I did R this time, or no, SAS for everything, because, why not? Same thing in, yeah, this is where it gets tricky to parse these, but those are the three new, what appear to be interaction terms that are not their main effects added to the model right there. Everything else is the same. The only difference is that to do, I'm also going to add some comparisons across the affected gender to see if it differs by person. So the differences are linear combinations. I did that in Stata with these three LinComs as well. Let's see what happens. So correlation pattern largely the same after controlling for gender. Is there a difference in the gender effect across the three people? Nope. However, here's what we get.
Go back to the GLHT statement.
Yeah, let's go back.
Do we have 3 of them or 2 of them? Because we were doing, we were kind of grouping them to compare mom and kid before. Okay, so it's still just mom and kid. So
Yes.
we still somehow have a reference group. Dad is still the reference group?
No.
No.
There is no reference group.
So why do we have 2 groupings?
So this is the gender slope different between the first outcome and the second?
So dad and kid?
I think it's kid and mom in this way. Yeah. And then is it different between, this would be kid and dad?
So it's like it's listed by dyad.
So it's,
Yeah.
You need a C for each dyad.
Yeah, and so you only need 2 out of the 3 because the third's redundant, once you know the first 2.
So, Rebecca, I think
there's
with,
still a reference group?
There's not a reference group in this model.
you have the first 3 zeros because we have, in effect, 3 different intercepts that we're
Yeah.
turning to 0 because we don't want them to influence how we're checking between the slopes of our main effects, which are the second group of 3.
So the logic here is that this is the effect of gender on the kid. This spot is the effect on mom. This is the effect on dad. I'm not asking, is there an effect? I'm asking, is there a different effect depending on which person you are? So I have to set up a difference because it's not in my model. What I have in my model is the slope for each. So this is a difference in slope between 2 pair, or 1 pair, 2 people, and this is 2 different people, and it doesn't matter which ones I pick, by the way, because I just need 2 out of the 3, and the third is determined.
So it's contrasting effects across subgroups.
Yeah, so it's creating 2 differences, and then it's testing those differences simultaneously. To answer the question, is the effect of the adult child's gender different based on who's answering the question? And the answer is no. However, if I go into the output more specifically, that's kind of misleading because here's my 3 intercepts. Now, kid boy is 1 if the adult child is a man, and it is 0 if the adult child is a woman. So what do we learn about adding main effects? What happens to the intercepts? They're conditional on the 0 value of the new predictor. So these are the intercepts for each kind of person in families in which the adult child is a woman. In that kind of family, yes.
Lisa, can you go back to the GLHT thing?
Sure.
Because my understanding in the first one, scroll up please.
This one?
The other one, the one comparing, yes, exactly.
Okay.
So my understanding there is, given that we are getting two differences, to me, in that case, we are stacking both. That's like a multivariable test, so we
Correct.
are not testing if those differences differ to each other, but if both things, any of both are different from 0.
That is correct. I'm testing both slope differences simultaneously against 0.
Okay,
And yes.
so, but you said that with that test, we wanted to see if the differences in dad or mom was different to the other effect, which to me is not the same thing.
Yeah, so I did down here, did them one at a time. So like this is the difference in 2 of the slopes. This is
Okay.
2 more, and then this is 2 more. And then I did some stuff that just to show you what you could do. Fractions.
Oh, shut up.
Yeah.
Oh my gosh.
So what I'm doing today in these is I'm lumping, because these need to have a 1. So I did half and half, mom and dad. I'm basically averaging the slope. And then I'm asking, is the kid's slope different than the average of the parents?
Is this the interpersonal effects?
This would be, it's not yet doing this. That's
Okay.
that's coming in a subsequent model. But this is just showing you that you can lump things together in various ways, however you want that's going to answer your question.
Does it have to equal 0? Because you have like a -1.
Yes, yeah, it has to sum to 0. Yep. Yep, and in Stata, it wouldn't let me do fractions, so I did it in a roundabout sort of way. So like this one, I have -2 for the kid, and then 1 and 1 for the mom and the dad, and then I took the whole thing and multiplied it by 0.5 to divide.
I thought fractions were bad, but Stata's worse.
This was another tip that, so I have just like random people who find my YouTube channel and like try to learn from me, and then they send me emails with questions and stuff. And every now and again, like I think I complained like 2 years ago that I couldn't figure this out in Stata, and like someone wrote me and was like, you can do this way. And I was like, thank you.
So you basically you doubled your effects and you have it where you wanted it.
Exactly. Yep. Because it's gotta sum to 0, but how you get there is up to you.
So let me see if I can understand what would that mean? No, I don't. Why would you want to do
Fair.
that?
Why would I want to do that? Pedagogy is reason number 1. Number 2 is that if I'm thinking about like mom and dad as a unit, and I want to know if the effect of gender on the parent is different than the effect of gender on the kid, then I got to lump the 2 kinds of parents together.
So you could technically weight mom more heavily than dad or vice versa.
I could, yeah. So situations in which you might do this, like let's say that you have a treatment study where there are 3 treatment arms and 1 control. And you just want to know, did treatment work? You'd like 1/3, 1/3, 1/3. Like put those together and then compare the mean of those to control. And then you can ask more specifically about each treatment. But sometimes you want to lump stuff together.
Cool.
I know. I thought so. But anyway, we're packing up. We got to go.
Sorry.
He's like,
Subtle hints.
it is 3:13, so that is an appropriate time to say, we're done for the week. We'll pick this up next time. I'll let me show you where we're headed. Let's spoil the surprise. This is where we're headed.
Oh.
Okay, this is where we're going to end up. This is your very first
Wow.
path model.
Okay.
So let us know if you need help getting homework 4 done. Vladimir has office hours tomorrow.
Yes.
I will have some on Monday that end in 4:10.
Is that a
Email
lot?
is fine as well.
And so we're doing a lot of this, what you're showing this fall.
This
or
is not this fall.
Oh.
So this is path analysis that doesn't show up again until structural equation modeling class.
Oh, okay.
I think I had one example at the end of clustered, but by then no one was paying attention anymore, so I didn't really go much into it. Multi-level path analysis is where that ended up. But anyway, all right. It is not garbage day, which means have good weekends. Let us know if you need anything. Thanks for being here. Bye for now. Lisa, out.
Bye.